All right, my name is Rayees Pasha. I lead the product team at RisingWave Labs. First, I want to thank you guys for taking the time out to come on a Saturday morning. I know there's a bund, and I'm just impressed with the turnout that's come here. And especially a special thanks to E6 Data guys, our partners, for setting up this event. In terms of agenda, I'm going to talk about three things. One, quick introduction to RisingWave. I know a lot of people may not have heard of it, so I just won't go too deep, but especially positioning wise where we are and what's new that we're bringing to the market. Then second, since the theme of this meetup is lakehouses, I want to see what is the convergence of a stream processing database with a data lakehouse? How did our journey start? What have we done so far? And then the bulk of my talk, the last part, which is basically building a managed Iceberg service for streaming workloads. That's the big project that we undertook a few months back. And we're going to roll out some feature updates with that. So I'm going to talk through some of the key features and design decisions we've had to take. So this is going to be a fairly high-level talk. So it's a broad topic. There's a lot to cover. So feel free to stop me if you have any questions. But I think if you need a more deeper discussion on a technical level, I'm happy to point you to the right people in our team. We're an open source product, so everything's out there for you to see. So as a way to introduce our product / company, we are a young startup. We've been around for 4 years now, founded by Ingjun Wu. He's a database veteran. After doing his PhD in Singapore, he was working as a postdoc researcher at IBM Malmeden. So two of his research interests were, one was stream processing and another was distributed databases. So the genesis of RisingWave came about because of this convergence, because what he saw was the stream processing, the first generation systems were not taking advantage of a lot of the innovation that was happening in terms of how you deploy, how do you scale, how do you manage and deliver this as a service. Part of the reason was that stream processing was a niche, and as it has become more and more democratized over time, we saw an opportunity in terms of business, right? So that's why the company was founded in 21, and then we open sourced it. We have a liberal license, Apache 2 license, so any one of you can fork, you can contribute, you can use. So it's from a use permission perspective, we're very open in that sense. And our core mission was always about making sure that the shift towards stream processing as a trend is not a niche, but more to cover more and more workloads, because we don't feel like it's a binary choice between stream processing and batch processing. Almost that's how the general thinking is, but what we see is as more like a spectrum. So anything that you could do with, not everything, but most of what you can do with batch could be done with stream processing. It's just that the tooling wasn't there. And now that the tooling is coming on, so if you haven't considered stream processing, you should take another look at it. So in terms of where we are, we are a community-driven product, right? We are pretty active in the community. Some of the stats I've put there in terms of our GitHub repo, in terms of the number of contributions coming from outside, in terms of we have a vibrant Slack community, about couple of thousand or more to 3,000 people in the community asking questions, learning from each other. But the true test is the deployments themselves. We are a totally containerized application, and we see that month over month, we see growth in terms of how people use it. Now, these are people who are using RisingWave for prod, dev, pre-prod. So we know at least 300K Kubernetes clusters have been deployed using RisingWave, with active deployments of 4K happening every week. So it's a very vibrant community, and we get surprised in how people use RisingWave in some sense. So it's a lot, and that's a very good way for us to know in terms of product market fit at what are pain points we're addressing. In terms of paying customers, we do have, and some of the logos I've listed here, they're all using it for mission critical applications, things that obviously require ultra low latency. We're talking about millisecond latency. And the team background, a bunch of database veterans, practitioners. So a lot of the core functionality is built from the cumulative knowledge that we've gathered from different places. So in a way, our secret sauce is the team, a bunch of engineers doing hard engineering. So in terms of the product, so this is sort of the high level overview of how the product, what pieces that it interoperates with. So think about RisingWave as a distributed SQL streaming database, right? At the heart of it, it has a compute engine, obviously, that does the stream processing for all the event data that gets generated. But we also have a storage engine purpose built for high velocity data that allows you to serve the data as soon as the processing is done. So from a paradigm perspective, typically you have databases which, from a batch processing perspective, you bring in the data, you store the data, you do transformations, and then you prepare it for serving. In our case, because of the paradigm of the incremental processing model, the arrival of the data will automatically kick off the processing. So in a way, your data is ready to serve the moment it has been processed while it's in motion. So we use tiered storage. So the data gets stored first in memory, and then obviously it gets placed in different layers. So in this architecture is what enables us to guarantee latencies of like milliseconds, 10 milliseconds, 20 milliseconds, 30 milliseconds. Even if your streaming job is complex as a multi-stage job, we can still guarantee that because of the in-memory architecture that we have built. And then another thing, from the data model perspective, we are pure SQL. So you don't have to learn a new thing. If you know SQL, you can get started in minutes, right? For us, every stream, think of it like a base table. If you're working with a traditional database, you have a base table, you create indexes, you create views, you join them, you filter them based on SQL predicates. That's exactly what you will do with RisingWave. You don't have to learn a new thing, right? So that simplicity, that's why I was saying when you were asking like there's no access to low-level API, that's a conscious choice we made, that we could open it up, but that would be catering to a different persona. Our persona, we know very clearly, it's going to be a SQL developer. And if SQL is not sufficient for you, we do provide you with a UDF framework to write your own code in multiple languages. But that's about it, right? If you open up the low-level API, you're actually hurting because you're giving them something tool that they don't know how to use. So I do want to make a mention about the Iceberg part because this is the theme of the talk. So from Iceberg perspective, our journey started a few months back, where we provided ways to bring in the data from Iceberg as well as write it back to Iceberg. But what we noticed with some of our customers was that it's still, our involvement required to be more than that, because the data lifecycle management of Iceberg tables was something, a burden we pushed it to the user, assuming that they would be able to take care of it. And that kind of created a lot of friction. So I'm going to talk about that part later in the talk, but just wanted to mention the right bottom corner, what you see there. So let me pause here for a second, see if you guys have any questions on at least the high level overview of what RisingWave is. No? Okay. So in terms of the use cases, we're agnostic. We're a data platform, right? So it can be any industry that could apply to. Like I've listed 3, but you could pick your own choice, whichever makes sense. So for example, with fintech, these are actual use cases of where people are using our product, right? Like real-time fraud detection. If you are a stock exchange, you're doing post-trade analytics. You have dynamic pricing. Some of our e-commerce customers use it to do the search pricing sort of a model. And then IoT, right? If you have data that's in the field, you want to bring it in, and you really don't have any time. The basic assumption is that data has shelf life, and you need to act within a certain time before it loses its value. That's sort of the core sweet spot for us from perspective of what workloads we are best suited for. So yeah, doesn't matter what industry, but as long as your requirements demand that, we're there. Now, how do we do that? How do we guarantee that we are sort of the best in class engine for stream processing? That's at least the claim we make, right? And we have benchmarking data I can share with you. The 2 key aspects, is a bunch of features, but 2 I will highlight. One is the state management. State management is really critical because in stream processing, if you're doing stateful stream processing, it is important to capture the state of what changes happened in the data, because you're trying to answer a question over a period of time. And that requires intelligent handling, because you're not only taking a snapshot of the view of the data and then answering a question, but you are answering a question as it's like you're replacing engine while the car is moving. So you need to know how to handle all of the complexities that come with it, right? So in our case, we built in advanced features to handle large state. Even if you have a a windowing function that spans 24 hours, and you have a complex pipeline that stores a lot of intermediate state data. We know how to handle it. We know how to spill to disk without, causing crashes and things like that. And the second thing is also the backfills, right? Like with stream processing, this is a continuous running job. It's not like an ad hoc query that you run and then say, okay, I'm going to run again. The query is continuously running, so there's no downtime. You almost have to, if you have to reload the data, reprocess the data, you have to have parallel infrastructure. So we have added adaptive scaling. For example, if you say you're running a stream job and you brought in there's a certain spurt in data and you want to process that, because of our cloud native architecture, you can adaptively, as you throw more hardware, it'll automatically, as you start using those additional codes, right? And then the third thing is the consistency and guarantees that we provide, right? This data is ephemeral, it keeps going. It's like when you look at streaming data, you don't purchase the data because it has a short shelf life, as I mentioned. So the system has to be able to provide some guarantees in terms of persistence, and we've implemented a fast checkpointing mechanism to do that. And the second thing is, it's not just for read. We have added separate paths in terms of workloads, that if you have a mix of both read writes, the system is able to understand and apportion the right amount of resources to handle each of the workloads. And there, I think, to the point earlier was mentioned with E6 data, like disaggregating compute, the same model we have used internally to disaggregate compute, purpose built for streaming versus querying versus compaction. So you have knobs to tune to assign what you feel is based on your workload needs. And then I think I talked about the tiered storage, which is, it's a very common architecture pattern now. And then advanced feature set, right? So temporality is very important with streaming workloads because everything happens in the context of time. So every event has a time, and every event goes through a processing timestamp. So in that, it's important to know the order in which the data arrived. If there is late arriving data, if out of order processing, the system should have the sense of addressing all those concerns. So we have added a bunch of features, some of them like for time and order, watermarks, windowing, all of the things that Flink provides, we have like for like functionality. And then schema evolution, because of the way API upstream sources change, your system should be able to handle and tolerate those changes. So we have support for schema evaluation to automatically detect changes and apply them. And then if you're doing ad hoc querying, we have support for time travel, as of joins, things that actually allow you to go back in time and make connection to what's happening right now with your stream processing. And then, of course, I talked about user-defined functions, which are part of a standard feature for all the tools now. So architecturally, I think, I know I don't have too much. I'm going to spend only 30 seconds on this. The three key things that I want to highlight is the engine itself, right? Because it's a distributed streaming engine, purpose-built, written in Rust. And this is not some bolt-on implementation that we took and said, okay, we're going to do something and then open source it. No. This is, every line of code is brand new that our engineers wrote. The second thing is the architecture itself. Now, cloud native is such a buzzword. Everybody uses it. In our case, obviously, beyond the obvious things like separation of compute and storage, we've gone further in terms of implementing disaggregated compute, really fine-tuned, elastic scaling of resources that you can provide, and also serverless capabilities for some common tasks. Like, for example, for compaction, for backfills, all those, you don't even need to assign a compute. Automatically, we will determine the pressure and then assign adequate amount of resources. So all of these modern solutions that have been maybe not invented by us, but we have adopted all of those, so that what you get is the latest and greatest in terms of best practices. And then the last thing is the open ecosystem. So we're not part of a separate ecosystem, and we're not part of a separate ecosystem. We are part of sort of, the way I put it is, we are Postgres wire compatible. That opens us up to any tool that's, we're a drop-in replacement. Basically, if you're using Postgres, say you want to try RisingWave, it's just you don't even have to test. It should work automatically, right? And similarly, on the technologies on the upstream side, we're not Kafka specific, Pulsar specific. We are open to any tooling, like any CDC streams, they should work automatically with our system. Okay, so switching gears a little bit, That was about stream processing, streaming databases, what our core competency is, right? So where does Lakehouse come in? Because we're not a Lakehouse vendor. We, with our early adopters, we saw a number of customers like, hey, we are going to Lakehouse strategy. We are going to store data. You are our stream processing layer. How do you integrate? So that led to us to creating source and sink integration first. For those who are not well versed with the terminology, source is basically your upstream system that's pumping the data. That RisingWave is the consumer of the data. Sink is the destination where after processing you push the data, right? So in a way, Iceberg was both a source for us as well as a sink. We are the cog in between that does the transformations. So for that, it was fairly straightforward. But what we ran into is, as we implemented, we ran into a lot of the drawbacks because Lakehouse architectures are purpose built for batch processing, right? Because that's the predominant way people process the data. So it wasn't meant to, in a way, address some of the later new things that have come about. So I'm going to talk about few of those pertinent drawbacks that we saw and we heard. This is not just us saying, but we heard from our early adopters. One was, if the data was fast changing, there was no support, like there was no tooling that allows us to users to use event-driven computation semantics. So which meant you really had to use batch processing model for even if your data was fast changing. So the time it would take for you to take action on it would be predicated by not so much what your data characteristics were, but by what the tool you had. So that was one problem. Second is, from the data serving perspective, if you had a complex query, because of the fact that you couldn't adapt to the fast changing data, your latency requirements went through the roof. So even though you had invested in RisingWave to process the data, but you couldn't really take advantage of it because of the model, because of the lack of proper integration. And the third thing is the complexity. Say, for example, you have different types of workloads all running on the same data lakehouse. To make it work, you need like really sophisticated data engineering. You need a team that understood the nuances of how the event data is processed and then how it's stored. How do you convert data that's meant for operational to more analytical use cases? So the burden is on the user now instead of us, right? And the data inconsistencies, right? Like you have single copy of data. How do you ensure that the guarantees that upstream systems provide are carried through all the way to the destination? And then last but not least, the cost, right? So if you have to do all this, you have to have an army of engineers or sophisticated technologies. It just the cost would balloon up. So what we did was, okay, so how do we address this? So we started with a notion of a streaming data lakehouse, right? This is not probably a buzzword again. There's no standard definition, but at least the way we see it is a lakehouse that treats streaming data as a first-class citizen, right? When you come in, you bring in the data, you ingest it in real time, you process it incrementally. So your posture is, you use the mode of processing that you do with streaming workloads, you kind of adopt it for your data lakehouse also. Now think of everything as like a stream. It's like everything is. I didn't mean to make it sound zen, but the idea is it's just a mindset, right? People have a difficulty assuming what stream is because they think, okay, why would I need a stream? Like if you think of even your batch workloads, can be reimagined as basically micro batches, smaller chunks of data as opposed to a large chunk. So what the size of the chunk is something you can determine based on your requirements. So in a way, you could reimagine all of your ingestion and processing could be just as a stream processing model. And the outcome is some of the customers were implementing medallion architectures. You've heard of shift left, all these trends. It fits really well with this architecture because you're trying to push as much as possible the processing upstream, and you are clearly creating tiers of data like bronze, silver, gold. In a way, you can provide clean hygiene between your data sets so that what can be used for what purposes, all that becomes easy with this sort of implementation. So let me talk now, before I go into the full managed service, I want to talk quickly about what we have done previously, like 6 months, 1 year back, in terms of basic integration between Iceberg and RisingWave, right? So this is general architecture of what the top part is what we usually do with any customer, right? You have data coming in from Kafka, from relation databases, real-time data coming in, and they do some processing, and users typically push it to some BI dashboards or could just push it to another destination from which they serve the data. Now, Iceberg came in, and then we said, okay, we'll have to provide some way to read this data at least as a batch source. And then if you are doing some data enrichment where you not only take the data from Iceberg and then you are marrying it with some sort of enrichment logic from the real-time stream, and then you can write it back to Iceberg, right? So sort of the simple workflow that we did. It didn't. The idea was just to fit in with what customers already have, so that they can leverage the stream processing capabilities. And we followed the same model of pure SQL. The notion for Iceberg was just another type of source. So for those who are not familiar, for us, source is like a unwanted stream of data. It could be from a CDC stream, could be from a message queue. So we treated it the same way. Even though this is historical data, we use the same semantics so that people don't have to understand a different API. So in this example, what I'm showing here is an Iceberg source. We have some the warehouse path, and it obviously is hosted on S3. And when you run this source command, all it does is it maps the Iceberg metadata to RisingWave, and we store that as an object registered with RisingWave. Once you do that, obviously you can do querying directly. You can do a select star. You can do an insert select to read from your Iceberg source into RisingWave, so it becomes a source. If you want to do any enrichment, you can do it as if it's running on RisingWave, right? And you can also push it back. Like the second part of, if you have real-time source coming through from Kafka, for example, and say you want to do you want to push all of the data and store it in an Iceberg, you could just do a create sync into, right? So idea was simple integration, remove friction, so that you could just provide interoperability. And under the hood, basically, you're looking at it's a very simple implementation. Front end, which happens to be our query planner, will just fetch metadata from Iceberg source and looks at what are the actual files that need to be read, and it parallelizes the operation, sends it to all the compute nodes, and in parallel you read. And so it depends on how large your cluster is, your throughput will go through, and you read the files, and that's it. It's as simple as that. And on the sync side, which is on the destination side, it's much more popular because a lot of people use Iceberg as a sync. It's again very simple. You write a create sync statement, and you mention that the connector is the Iceberg here, and then you specify the parameters, like where the warehouse is, what's the catalog name, and all that. Simple, run that statement, and then automatically your sync will get all of the updates from the upstream data. So again, implementation wise, it's fairly simple. One thing I wanted to mention is we did not implement any of architecturally in terms of a query planner, in terms of how the execution happens for Iceberg. We reused pretty much everything that was already built into our product. For basically, it's another extra use case in terms of how we read and write data. In the one thing I would like to mention on the details wise, like our write capability, we were using the merge on read mode for basically handling updates, deletes from the upstream source. But otherwise, it's the writing and the compaction, checkpointing, all of that is no different than how we would do with a regular RisingWave table. Okay, so now I'm coming to the sort of the main part of the presentation, right? Like it was all good. We created sources, we created sync. So you had stream processing, you were taking advantage of both the systems. The behind the scenes, there was a problem because all the data that you're accumulating, you had these Iceberg tables. The assumption was that the customer is smart enough to know the compaction strategies. They had a solution in place. They were using Spark or some other solution, or they also were using some sort of a catalog. They knew how to handle the metadata. So it's almost like they were supposed to be the experts to handle this. What happened is that was not the case. Now the customer said, we don't know how to do this, or we're using like EMR for compaction, we're using Glue for catalog, and we have had to talk to multiple people to address a single issue. We couldn't find, everyone wants single throat to choke in some sense, right? So we were like, okay, then what is the problem? Either we get out of this business of adding support for data lakehouse, or we do something more. So we chose the latter because we know where the trends are, right? So for us, there's no way, but we have to provide support for data lakehouses. So that's kind of the genesis of this managed Iceberg service. So I'm going to still start with a piece of code because I want to show you the flow of how the service would work through, right? So we introduced the notion of a table, Iceberg table, similar to a RisingWave table. It has the same semantics, same syntactic structure. The only thing is you mentioned something called engine equals Iceberg that automatically tells the system to create a table in Iceberg directly with bypassing entirely RisingWave execution path. And we retain the notion of connection, which is we have for source and sinks. The connection kind of captures the metadata behind where the particulars of the parameters required for this Iceberg table. So you can mention obviously the what type of catalog it is, what is the location of the catalog, the warehouse where it's going to get stored, and if you have security, for example, access key, how to access the data and all that. Once a connection is set up, your tables you can create it, and you can have multiple connections, which means you can have multiple catalogs and warehouses managed by a single RisingWave system. You can just set the alter system parameter that will allow you to have multiple. So in a way, it opens you up to having multiple databases, and those databases having different objects using different catalogs, different warehouses. And your RisingWave cluster will be a single point through which you can push data. Like your upstream data may carry from different sources, and you may want to compartmentalize the data into different databases, different ways. So this simple architecture allows you to do that through simple SQL, right? You can just configure a connection, and then from that point onwards, it's just you're dealing with regular SQL. So what exactly that just running that command was a simple command, but it required a lot of work for us to do in the background. So what sort of features did we work on? One is the auto compaction. Second is the support for Iceberg catalog. Now there's different types of catalogs, obviously, that we support. And then some of the other features that are required for us as the value add. Like for example, materialized views is a key feature that we support, incremental materialized views. We implemented that on Iceberg. Table sharing, so that once you have Iceberg tables, they are open format. That way you can use the engine of your choice for querying. And then our merge on read implementation to actually take care of the changes in a consistent, in a performant way. And then the streaming ingestion. Earlier ingestion we did with Iceberg source was batch upload sort of. This is more granular, so you can do the streaming ingestion. So I'll start with. Let me see how am I doing with time. Okay. Yeah.
You can ask questions in between. It's not like that you have to wait till the end and then ask the questions. Those who have worked on the streaming, they know how much pain it is to stream the data and then load it to data lake or even data lakehouse with all the small files and all other things. So feel free to ask the questions even in middle. No need of like waiting in the end and then having the questions.
Yeah.
Any questions till now?
Yeah, please.
How do you handle backfilling? That seems to be a pain for real-time versions.
Yeah. So the question was, let me repeat her question. How do we handle backfilling? Right. That's a great question, because each time with the streaming jobs, as I said, they're continuously running jobs. There is no notion of alter this job, because when you have to alter, you have to stop the job. Just I know you probably know, but I'm trying to giving the context to people. So the way we handle that is we allow you to create a parallel job, a backfill job, and we have a command called alter swap, where say you have a streaming job S1, and the S1 needs to be changed because the business logic changed, or you added more columns, or that quality that you've discovered a data quality issue, something was bad, so you want to reprocess it. So you create S1 prime, that does the backfill, because you typically when the backfill you are processing terabytes of data, so it's going to take time. So what we have is serverless capability that will doesn't use the regular compute that's for streaming jobs, so that it doesn't interfere. You prepare, you do the backfill, and then you run this alter swap command that in an atomic fashion will flip it. Your S1 prime becomes S1, so that the rest of the pipeline you have doesn't get affected. So in a way, it's like a trick we play, but we are trying to add actually a more in place update. So we don't have to play this trick. So you can say actually alter S1, and we should be able to handle that. But it's a engineering challenge at this point, because it's not easy to do that, but we're trying to solve that. Yeah.
So my question is again back to that low-level access. You did mention about UDF from the time I've been using RisingWave, what I remember is with UDF you cannot access external sources, right? Like you cannot access API.
Yeah.
So is that a design choice, or is there something on your mind in your roadmap for the long run?
Yeah, a great question. That was a poor man's choice at that point. We didn't have the resources to build. So soon we'll be releasing embedded UDF based on Rust with the VASM implementation. That will have basically bidirectional access. So you can read the external sources, you can bring in. So I think, I can share with you the details, the PR that should be coming out in a month or two. Because right now our implementation, as I said, is not, it has limited utility. With this, it's really going to address your question actually.
Thank you.
Yeah.
So earlier you had mentioned that you had solved incremental materialized views. So these were RisingWave's materialized views or Iceberg's materialized views?
These are Iceberg materialized views. Yeah, I'm going to talk about, I have a slide on that, because the incremental materials have been there with RisingWave forever, right? That's our key feature. Now we wanted to provide parity of that feature with Iceberg also. Yeah. Okay, so I'm going to try to run through fast because I have a, okay. Yeah, if you want to ask you, that's fine. I don't want to interrupt you. You have a quick question? Okay. So, so the key decisions, key features that we implemented, I want to go through fast, one by one. The compaction, as you know, compaction is critical for any distributed system. You have a lot of small files, especially, they create, not only they are a burden on the resources, they also create pressure on the metadata services. So that, and if you don't have a good compaction strategy, obviously, it's self-evident that it's going to cause problems. And obviously storage costs will go up, just the stability aspect of the product itself will be in question, right? And we do this well with our current architecture. We have compactors, that's a separate service that runs in the background and takes care of the fragmentation in data, all of that. We basically brought in the same infrastructure to handle with our Rust implementation. In the case of our solution, we're trying to address the problem that are with the prevalent system. Like if you have Spark dealing with JVM, dealing with the complex tuning and the parameters, all of those pain points that we know, we're trying to avoid that with our implementation. In our solution is Rust based. RisingWave is written in Rust, so that was a natural choice. And we use DataFusion as our processing engine to basically handle compaction under the hood. And
the compaction happens continuously, it is happening, or you are based on something that, okay, after this much of time or after this much of size, it's a continuous process.
It's a continuous process, independent. The customer, there is some tuning parameters. Like for example, if you have a write-heavy workload, you can set up what the checkpoint intervals are, the file size is. There are some things, but for the most part, we don't tell customers to handle that part, right? We let the system handle it automatically, because we have serverless compaction in which where once you set it up, it will know exactly what the trends are, right? Upstream, it knows that there was a lot of churn in the data. There was a huge batch of data came in, so that automatically the system will realize that I will need to ramp up my resources on the compaction side. These are the kind of things that the user will not be able to know, right? They themselves are not familiar with it. This is a runtime decision basically. So
doing behind the scene in the
yeah,
same job itself.
in the same, yeah. So there's a separate service called compaction service that handles it, but how that communicates with the compute nodes is not something that the user need to know, because it's sort of a low level detail.
Why
Yeah.
I ask these questions, because at Walmart, we used to use Apache Hudi and we used to use MOR in the streaming presence, and it used to be very, very tricky. Like when the compaction is actually hitting, and sometimes it used to work, and sometimes it used to literally sucks. Like all the small file issue, and we used to see that, okay, sometimes it's like really, really good, it's trying to come back. And then we realized that actually our existing solutions, like the solution for merging the small files using the normal Spark based solution, which we used to kick in all our batch pipeline, was much better than using something inline compactions. It was good, but not I can say that it was not really, really good. So
Yeah.
are you also getting this type of things from your customers, or your customers are happy with this compaction, and that too in continuous fashion, and that too in streaming
Yeah.
with the MOR tables.
Well, I have to caveat my answer by saying that this is a new feature, so we don't have a lot of customer input on how it is. But we have done internal testing, benchmarking to see how well we handle small files, and the tuning that we have done. Some of the recommendations I talk about were based on those experiments, right? Like how because streaming systems are very granular, right? Our checkpointing happens much quicker, and the compaction is very aggressive with the file sizes, block sizes that we use for Iceberg tables is much larger, so it required a different set of parameters to be tuned. Now, that's the feedback we would like. If you try this and you say, hey, this sucks because this issue, we'll fix it. But yeah, at this point, we're more in a, I would say this is a beta version that we're going to release.
Anyone or anyone have used this? Any comment for that? Not yet. Okay.
No. Okay. So I'm going to skip over that architecture diagram because I'm going to be cognizant of time. Catalog, right? Catalog has always been a journey for us. We started with basically JDBC catalog as our to store the data. The rationale being that it reuses our existing infrastructure, because that's what we do for our RisingWave tables. All of the metadata is hosted in Postgres backend database. It worked, but the problem is community doesn't like it. They say JDBC catalogs are a no-no. So we said, okay, we'll build a REST catalog, but that's a choice we provided. And for AWS customers, if you want to use Glue, we support that out of the box. And when the current version which required a lot of our work, which is what we are, that's the sort of the default catalog, is the REST catalog based on Polaris, right? Our goal is to be open, right? You pick a choice of catalog that works best for your workloads based on your data stack, and also the cloud. We are across all clouds, AWS, Azure, GCP. Basically, the idea is whatever data lakehouse you use, and if that comes with a specific catalog, you go with it. You don't have to rely on us to make the recommendation. So yeah, in terms of implementation, this is a question. The reason I included is because Rust SDK is not mature enough, right? So we started the implementation with the Iceberg Rust SDK, and some of the functionality was missing, so we had to go the Java route through the JNI. And so just if you are the kind who go into the code and look at what our PRs look like, you'll see a combination of both SDKs being used. Okay, so incremental materialized views. So this is to your question about how we do the benefits are, everybody knows that the materialized views are the abstraction layer that allows you to maintain updates automatically as the data comes in. So this is something that's already been there from day one in RisingWave. So we're just bringing that to the Iceberg table format also. So basically, implementation wise, we track all the snapshots that are there and see what new updates have happened. And then we scan and find what the new files are, and if there's deletes, whatever the absurd operations are there, we apply them. There are some limitations in our implementation right now because it's the first version. It doesn't support insert and only supports inserts. The delete handling is still being worked on. So we plan to have much more robust support in the next release. In terms of the freshness, the commit frequency is important here. The reason I'm mentioning is because with our RisingWave materialized views, you can guarantee millisecond latency. With Iceberg, it doesn't work because of the architectural pattern. So what we guarantee is, at least the tuned version is about 1 minute. If you want something sooner, there are some workarounds to do it, but that's sort of the default where we are standing now. Yeah, I'm going to skip just to save some time. Table sharing, right? Again, table sharing is a key feature that allows you to use any engine of your choice once you have built those tables. For RisingWave, for us, the challenge was how do you open access to the users while keeping the access control to both the metadata and the actual object store data access, right? And we reuse some of the same components that we use for RisingWave tables. The Postgres compatibility came into handy here, right? The connection strings that we already support for RisingWave, the same we're going to use for Iceberg also. We created two new system tables, one called Iceberg tables and table namespace, that captures all of the metadata related to the Iceberg tables that are managed by RisingWave. and you can just query that directly. We provide some high-level interface through a UI, but if you want to query, you can use just standard SQL to get information from those tables. And in terms of access control, we already have built-in permissions. RBAC model, the same model will apply on Iceberg tables now. And then object store, we have a notion of temporary AWS credentials that allow you to that allows RisingWave to manage the data. And then we obviously don't provide access to the users directly. We assume that the users who are running RisingWave to access the Iceberg tables have some read-only IAM role permissions already built in. So that's the requirement we place on the user. So in terms of the systems, I listed only 4, but from a table sharing perspective, any query engine that supports native Iceberg table should work, because there's nothing specific about RisingWave how we manage Iceberg tables that will avoid that. But the ones we have tested, Trino, Spark, StarRocks, DuckDB, these were sort that we kind of started with, and we sort of the certified ones, I would say. But the rest also, Presto, others, you can try, and if you run into issues, let us know. If you obviously we can fix them. Merge and read. This implementation, just wanted to quickly spend 30 seconds on this. So for those who are not familiar, there's merge and read and then copy and write, 2 different strategies of how to handle updates in data lakes, right? So our implementation is on the merge and read side. We handle both equality and position deletes, and we use basically our engine, existing compute engine, in terms of how we process deletes. It's the implementation. Just if you're curious, it's a native hash join. It's an anti-left join to filter out what the deletes are. And basically the workflow is you ingest data files, you tag them, you enrich the metadata by sequence number and the file path and the position, and then you resolve the deletes, as I mentioned, through a left anti-hash join. And then one of the things we added that was which we see as a big problem was the memory bloat while we were handling the deletes. We have a notion of disk cache, which is basically object store serving as an extension of a cache, where we spill if there is a large update that's coming that needs to be processed. Okay, I have a few more slides, but this one thing I wanted to mention is the streaming ingestion, right? Earlier when I talked about our early support for Iceberg, that was more batch ingestion. So we added streaming ingestion, where if you have granular updates coming in real time, you can ingest data now. Again, the SQL is very simple. It's no different than what you would do with other RisingWave tables. And I've included links to some of the PRs. I know the way I'm talking about a barely 10,000 feet level. If you really want to know what our implementation is, if you're curious to see the code, you can go to the link and look at the PR itself. Okay, so this is the last section. I'll try to wrap up in like 3 minutes. One key question that comes up is the storage format, right? RisingWave by default is a row storage format. That's more conducive to streaming workloads because very write heavy and a lot of in-place updates happen. So that's why we picked that choice. But now, obviously for Iceberg, for columnar, how do we handle that? So we use the same our row store as our primary engine where we store the data. If it's append only, then we write straight to Iceberg tables. But if it is upserts, the upstream data has upserts in it, then actually the flow is it goes into row store and then it gets converted into an Iceberg table. So there are concerns obviously because there is some load, at least for the time duration when that transition has to happen. We are aware of that and we're trying to fix that. And then the reason why we picked this path is because we really didn't want to have a parallel architecture, as I mentioned before. We wanted to the same architecture that we could leverage for both streaming workloads and also for Iceberg table management. Okay, so exactly one semantic. This is one of the key things that was reported by our users who were early adopters. So in a way, we implemented the gist of this slide is we implemented a 2-phase commit protocol, basically to ensure that the copy of the data that's stored in RisingWave as a RisingWave table, and after conversion to Iceberg, there is compatibility and there's a clear consistency guarantees we can provide. So you can read the details in short of time, but basically this is one of the things that guarantees, so that when you perform analytics on Iceberg tables, the consistency guarantees that were provided when you ingested the data are carried through all the way. Okay, commit interval is again another key aspect, because when we commit the data with streaming data, which is high velocity data, it's coming in at thousands of updates or millions of updates per second, right? So the original engine we built for RisingWave was to handle that level of churn in data. Doesn't play well with Iceberg. So we have had to tune some of those things. Like for example, the checkpoint interval, we set it at 60 seconds. In the case of RisingWave, it would be a 1 second, even lower than that. So that's obvious. The reason for that is you don't want to have too much fragmentation, too many small files, right? So this is a compromise we made, some of this, but these are tunable. Like for example, if you want to go below 60 seconds, say I want fresher data than a 1 minute old data, you could do it. But the downside is your compaction blows through. So that's some tuning that you have to do for based on your workload requirements. And even with the 1 minute refresh that we have, you could use flush command if you want to push updates in between. Say, hey, I'll live with 1 minute for most part, but there are special cases where I want to push for sooner, like fresh data. You could use a flush command to actually push the updates to make the data available right away. And then this is, I think, the last part, the consistency. I think I talked about it. Basically, the notion that you have two copies of data, especially for the upsert workflow. How do you ensure that the internal store for RisingWave and Iceberg are in sync? We have a protocol, we have a RFC there of how we ensure that consistency. I can add more details later, but basically the log store stores the offsets, and there is the pre-commits phase where we go look at all the Iceberg files that have been changed, and then we take a snapshot before we commit. And in that commit is stored in the Postgres metastore, and that's basically your Postgres metastore becomes a single source of truth to ensure consistency between these two copies of the data. So that's pretty much it. If you want to learn more, you can go to risingwave.com/lakehouse. That's a placeholder. It has some information now. We plan to add more details there in the future. All right. Any questions?
Do you have any questions? I think we have asked multiple questions in the meeting.
All right.
Any other questions, please?
Was there a question here? Someone?
How will you handle the back pressure while reading data from streaming?
Good question. Actually, so we have in the compute part, we will check what the throughput is, because the back pressure can happen in two ways. One, because you have a lot of data coming in from upstream, or your logic is so bad, like one of the streaming jobs is not optimized well, so it will create a backlog, right? So in both scenarios, we have basically signals to check barrier. We have a concept called barrier latency that tracks how fast this data is cycling through your system, right? If it reaches a certain threshold, we automatically detect the back pressure, and tell the upstream source, like if it's a Kafka, whatever it is, I can't take any more data. So it gets buffered there. So that's to ensure the stability of RisingWave cluster itself, because otherwise we'll run into out of memory errors and other things. So the actual implementation of what that mechanism is a little bit for technical data I can share later, but the general model is that.
Sir, we have seen Iceberg Rust. There is one PR open for offset support.
Mm-hmm.
So what is your take, like RisingWave? Right now we have seen a lot of activity on that Iceberg Rust instead of your Java is tricky, right?
Mm.
So what is your take, like by when do you think that this release might happen? The offset supports in the RisingWave case.
Yeah, so one of our developers who worked early on this, moved to Snowflake, and he's one of the key committers there, working on that. I don't have visibility because these are independent projects, right? People have other priorities. But our take is, Rust is the go-to language for data infra products. So I'm sure our folks will pick it up. But there's no coherent roadmap strategy that I see that I can commit and say, oh, it will be available next month or the month after.
Is there any tip that you wanted to give? So RisingWave is one of the major committer to Iceberg Rust, and also the open source version of RisingWave. So do you have any tips how to start with open source contributions, or anyone wanted to ask some questions? they have seen the open source code base of that?
Yeah, go to our repo. It's a public repo, GitHub. You can find there's multiple projects. It's not just the core engine. You could because core engine may be a little bit they need some technical depth. You can provide connectors. You can provide there's so many other things with our product, and contributions are most welcome. There's no barrier as such. We are not like Apache Foundation or anything. We are an independent project. Although our license is Apache too, but we don't have any high priests that have to bless. As long as the code is good, it works. It gets a +2. It's in. So yeah.
Yeah, that is the good thing. Even the CEO, whenever you write the article, it is connected. So when we started, I've written articles on Apache Aeroflight just I think 3 weeks or 4 weeks back. He will read it. He will send you the personal message, and they are very much active on Slack also, and also in the meetup too. Like Fenil was trying for that blue support in RisingWave, and like it's a really active group. So you feel free to connect. There was one question, right?
Yeah. So basically, we were talking about enriching data with some, Lakehouse Iceberg table and one of the streams. But what if we have 2 streams coming in and they're like K stream capabilities or KSQL DB kind of thing we want to do and then dump it into an Iceberg table? So how that works behind the scenes? We have to stream working on different rates and compactions going on.
Yeah, no, good question. So for us, you can have 2, 10, 12, 15 streams you can join. And the joins are not a single stage. You can have a multi-stage pipeline, right? The first stage could be where you join these streams. And then the second, they join with your Iceberg data. And because this could be multiple layers of cascading MVs, we call them. So you could basically encapsulate your logic in either one flat job or in nested job of 5 or 6 MVs.
So does that be taken care behind the scenes or that we have to do it like Java?
You would have to create the materialized view for that, but the plumbing, so to speak, like the output of one becomes the input of another, all that is handled for you by the system.
Yeah, Pasha, I remember one very interesting use case. So, for example, let's suppose you have data in Kafka in a single topic, but you want to write to multiple Iceberg tables based on some conditions and based on, let's suppose, customer ID. Okay, for one customer ID, I want to write into different Iceberg tables, and I cannot do partitions and then say that okay, my data is actually there in these different partitions. So, but the client is like, I cannot keep the data of multiple customer in a single bucket. You have to write into different Iceberg tables, but the topic will remain same. And we found it little difficult, actually very difficult with the RisingWave approach. So is there anything that, have you encountered this type of issue that any customer who wanted to write into multiple Iceberg tables, the sync is same?
Yeah, I don't know if we can go that granular in terms of pushing data on a single topic partitioned into separate Iceberg tables. I'll have to check, because we are much more coarse, right? If you have a topic of data, your stream coming in, the result of that stream processing will go into a particular Iceberg table. Now that stream has partitioning in it, and you have some filtering. It'll require some data engineering. It's not something that I can say, okay, here's a feature you can use.
Yes.
Right? Yeah. Okay. If there are no other questions, all those who ask questions, appreciate it. I have some swag. You get the first dibs on those first before the rest of the folks will get to use it. Okay. Again, I appreciate you guys staying here. Hopefully the talk was useful. Okay.
Thank you, Pasha.
Yeah.